Hey everyone, welcome back, and today let's solve Leetcode problem 2071 titled Maximum Number of Tasks We Can Assign. Just a quick FYI, because this is a hard problem and there's just so many different parameters to consider, and it's a rather, more complex algorithm implementation, this is going to be a rather longer video. So let's go ahead and get into the actual kind of a problem statement here. I'm just going to quickly summarize it. I don't want to read all of this. Effectively, imagine we have a list of tasks and they each require a certain strength to complete. We're also given a list of workers and they each have their own separate strength. And we're also given a limited amount of magic pills where each pill can temporarily increase a worker's strength by that strength amount, and each worker can take at most one pill. And what we want to do is assign as many tasks as possible to those workers using those pills optimally, where a worker can complete that task if their strength is basically exceeding the task requirement for the strength, right? It can be with or without the pill. So for the constraints here, we know that each task can only be assigned to one worker, each worker can only be assigned at most one task, and each worker can only take at most one pill. And for the actual numeric constraints of this problem here, we see that n and m, the length of the tasks and workers, are both going to be between 1 and 5 times 10 to the fourth power, which are rather large input constraints, hence why this is a hard problem. The number of pills that we're given are always also obviously going to be between 0 and m, because we can't have more pills than we have workers. That just wouldn't make sense. And tasks at any index I, workers at any index j, and the strength constant input is always also going to be between 1 and 10 to the ninth power, which leads us to the main observations that we really need to make to solve this problem in the most efficient solution. So, kind of like on a high level, how we really would solve this is actually a combination of binary search and also kind of a greedy approach algorithm, right? Where effectively we know that we want our higher kind of higher strength workers to take on the highest level or highest strength task, because of course the lower level workers just wouldn't be able to do that. And so sorting both the tasks and the workers in ascending order would help us actually efficiently match those tasks to the workers based on their strength requirement and strength value, so to kind of maximize the number of workers that can do things and that can finish tasks at their level, not too high but not too low. Right, so after we actually sort them, well, usually when we're sorting data structures or when we're sorting input, binary search is very relevant. And in this case, there is no difference, or it's no different, right? We will still perform a binary search on, in this case, the number of tasks that we have to assign, where the search range of the number of tasks, I'm going to call it k tasks, that's going to be between 0 to the minimum of the number of tasks and workers, right? That's kind of like the search range of the number of tasks we can assign to the workers. Right? And for each midpoint that we calculate in our binary search, we first have to actually check if it's actually possible to assign per se k tasks to k workers using at most the available number of pills, if we assuming we use all the pills given to us to actually be able to get all those k workers to do those k tasks. And to actually do that, we'll have a helper function, and that's going to be a kind of a greedy function where we try to actually assign the easiest tasks to the strongest workers, and we only use pills when necessary to always make sure that we maximize the number of tasks that we complete. Because for even the easiest of tasks, we know we have the strongest and most consistent workers with the highest strength values that can be able to do it, right? And we're also going to be using a DQ, also known as a double-ended queue. Basically, it's going to be constant time popping off and adding from both sides of the data structure to actually efficiently manage the tasks during the actual assignment and helper function, right? So let's go ahead and actually get into the solution to actually find the maximum number of tasks that we can assign to the workers. So, like I was just talking about, to actually implement binary search, we always have to, of course, sort our input arrays, and so I'm going to call the sort method on the tasks and workers inputs. So quite straightforwardly, I'll call tasks.sort, and I'll also sort the workers input array. Again, the whole reason why we're sorting them in ascending order is to actually allow us to do our binary search and allow us to match the easiest of tasks with the weakest of workers, and it's also very important for our greedy approach, right? And now let's actually begin our helper function here. And as I was talking about, it's really the whole point of it, as the name is going to suggest here, is can we assign this midpoint number of tasks to these k workers, where k is again our midpoint. So it's going to take in a parameter k, right? The whole point of this is again to check this helper function to actually check is if it's possible, or if it's actually possible to can assign k tasks to k workers under our given constraints with their corresponding strength requirements, and the number of pills that we have. So in this can assign helper function, this is going to be the kind of bulk of the code here. Let's first actually initialize our queue and integer variables that we need to help determine if this midpoint k value is possible to actually distribute as k tasks to all k workers. So I'm going to call it just task queue, and I'm going to initialize it to just be an empty dq or a double-ended queue, and I'm also going to initialize a remaining pills variable. This is of course going to start off at the number of pills we have, and we're going to decrease it from there, right? So the task queue is going to be initialized to an empty double-ended queue to actually manage the tasks during assignment as we actually assign them to different workers, and the remaining pills is really just the total number of pills we have available or left that we haven't used or assigned to any workers at each iteration of this can assign helper function, right? Of course, we're going to obviously start off with pills because we start off with pills, and we decrement them as we actually assign pills to workers that need them optimally. Now let's also initialize a task index here. Sorry, forgot to do that. Forgot to go on the next line. Sorry, I'm going to call it task index. This is going to be, of course, initialized to 0, where it's going to basically keep track of the current task, that we're trying to assign from our input array to the current worker, right? So now let's actually begin iterating over all the different workers here, and more specifically the k strongest workers, right? Because we know workers is sorted in ascending order, and so we know that the k strongest workers are going to be at the end of the list, and we want to prioritize them first because they have the lowest chance of needing the pills, and they can take on the hardest of tasks or the harder of tasks, and so we're going to iterate over the k strongest workers first. And again, we know that we sorted the workers list in ascending order, and so we really just have to go through like this. I'm going to call it for worker index, trying to make it as kind of self-explanatory as possible, in the range of the length of workers, and we're actually going to start off by subtracting k, and we're going to go up until the length of the workers. Again, we're basically going through the last k elements of the workers sorted list, because that's going to give us, in ascending order of course, because of that, the strongest or highest value k workers at the end of the list, right? So the last kind of ending k elements or k strongest workers. And for every worker index in this range, this is kind of like the main queue appending part and validating while loop here. I'm going to just quickly type it out because it's really a lot of code, and I'm going to explain it once I finish it. So basically, while our current task index, while that's actually still less than k, again, keep in mind what k is. It's basically the number of tasks that we have to actually assign to workers. So while we haven't actually assigned all the tasks, and tasks, sorry, I had two ands there, and tasks at the current, oh my, sorry, pardon me for all these spelling errors here, at task index, while we know that's still less than or equal to workers, sorry, I think it's workers, not worker, at worker index, plus the strength that if we actually add a pill, while that's actually a valid case, we're going to append to the task queue, I believe that's what I called it, yeah, task queue dot append, and we're going to append to it task at task index. And of course we have to then increment the index by 1, indicating that we've actually used this task or applied that pill, and so we're going to increment task index by 1. Okay, so on a high level, what are we really doing here in this validating while loop, if you will? Effectively, while task index is still less than the number of tasks that we want to assign, we add tasks to task queue that the current worker can actually perform with or without a pill. And this is why we want to start off with the strongest workers, because we know that they have the highest chance of achieving these high tasks without actually needing a pill, right? Because of course we want to do this as optimal as possible, and we want to maximize the number of tasks that we want to give. We want to make k as possible as we can. And we're going to kind of continue this until we've actually considered all k tasks or until the task requirement exceeds the worker strength plus the pill strength. If we know that's the case, well, then we know all the worker strengths after this are, of course, going to be lower because this is indeed in ascending order. And so if this doesn't work with a pill, we know that we can't keep performing pills to any lower workers, and so we have to stop, right? That's the whole point of this kind of while loop implementation, right? So once we're out of this while loop here, now let's actually check if we have any tasks left in task queue, right? So if not, task queue is a good way to check if it's empty or not. We immediately need to return false. We know that for sure because we know if that there's no tasks in the task queue, that means the current worker just absolutely cannot perform any of the remaining tasks, even if we do give them the pill and increase their strength by strength amount. And so we immediately have to return false, indicating that we can't actually complete these K tasks. It just isn't possible, right? Now, the second conditional, if we can actually use it or do it without a pill. And the way we can check that is if task queue at index 0, if that's less than or equal to workers at worker index, we know immediately we can add or pop left, task queue dot pop left. Right, we're basically just popping off the leftmost element from the task. It's quite straightforward, right? And here, again, what we're really checking here is if the task at the front of the queue, i.e. at an index 0, if it can actually be performed by the worker even without a pill, we don't even have to add on the pill's strength value. We know we can definitely assign it and just remove it from the queue, indicating that we've actually assigned this to a worker. We've finished or completed this task even without a pill. And we'll have another else if conditional or elif conditional in Python here to kind of continue on with this. Elif task, or rather I should say remaining pills, if that's greater than 0, we know we still have pills remaining, and so we can then pop from the task queue still, task queue dot pop left, and then decrement the number of remaining pills we have, of course, by 1, because in this iteration, we literally just used 1 to assign to the current worker. Effectively, if the worker cannot perform the task without a pill, but we still have pills left, we know the worker can still perform the task with a pill. We have to then assign the hardest task from the end of the queue to the worker using that pill, and then decrement the pill count, because of course we just assigned or used 1 more pill to the current worker to complete the current task. And finally, else, again, if none of these are possible, if the worker can't even complete it without a pill, or even with a pill, and we have no pills left, and the worker still can't complete the task, we know we immediately have to return false, because then, of course, we wouldn't be able to complete K tasks, because that's the whole point of this defassign helper function, right? If the worker cannot perform any task remaining, or we have no pills left, we immediately have to return false. And now, out of the for loop here, if we haven't returned false anywhere in the for loop here, meaning kind of it is possible once we actually finish iterating through all the K strongest workers in the worker index or worker input array that's sorted, we can then return true outside the for loop, because that would indicate that all K workers have actually been assigned tasks successfully, and the defassign function kind of has returned true because this K value is actually manageable, and the binary search would continue on from there. Now, this is it for our helper function here. Now we have to actually start the binary search. All we did was just initialize our def can assign helper function, but we haven't actually started our actual binary search on the actual input arrays to maximize the number of tasks possibly assigned. And here is where we do that. Now, of course, before we even start any binary search implementation, we always have to first actually initialize our range or set our range. And in this case, the range, I kind of glossed over this in my high-level solution here. It's always going to be initialized using left and right pointers, where left is quite self-explanatorily going to start at 0 as the minimum number of tasks, or as the least amount of tasks we can assign, and right, the most number of tasks we can do would be the minimum of the length of tasks, basically the number of tasks, of course, that we have in total, or the length of workers, right? Basically, we know that, of course, at minimum, we can assign at least 0 tasks. We can't assign negative tasks, of course, but we also cannot assign more tasks than the number of tasks or the number of workers. And so we have to take the minimum of 2 as kind of like our bottleneck highest range value or higher end value, because we can't assign 4 different tasks if we only have 3 workers because one worker can only do one task, and we can't assign 4 different tasks if we only even have 3 tasks because we can't assign things that we don't even have tasks for. That just doesn't even make sense. And now let's actually begin our binary search. This is actually really standard here. It's a very classic binary search implementation where effectively while left is in bounds of right, meaning while left is less than right. Our binary search current range is still valid. We'll calculate our mid value to be the sum of the left and right values, or pointers if you will. Integer divided by 2, hence the mid value. That's why we call it mid. And if we can actually assign this, if we can actually assign this kind of k or mid number of tasks to k or mid number of workers, if that actually has an output of true, I could say equal to true, but Python sets that as a default when I do that. So I'll just say if that's true, then we know that this is still valid. We'll try to push for even more tasks or even more workers and get left to be mid plus 1, or rather just mid. However, if that's not the case, if this is too high of a value, we can't assign this many tasks. We have to search for a lower, in the lower half for a less number of tasks, and update right to then be mid minus 1. And effectively, once the while loop is actually done, once the binary search concludes, once it terminates, we want to then return left. Why? Because this would be the maximum number of tasks that we can actually assign that's stored in the left pointer, right? So unless I made any syntax 00, which I honestly probably did, this should actually be a valid solution, and it should actually be accepted. So let's go ahead and double check that real quick. Like I was saying, I probably made a very silly spelling error of some sort or something like that. Okay, time limit exceeded. Probably made a really dumb mistake here, because I actually did submit this code just a few minutes ago, or just a few minutes before the video, and it was indeed working. So probably just a silly error on my end. Let me just quickly double check, guys. So feel free to just fast forward this part here. This is me just debugging my very messy code, if you will, but I do promise the actual logic and implementation is completely right. Don't think that it's not. So it looks completely right. I'm actually gonna, let me just zoom out here so I can actually see what I'm doing. While task index is less than k, and tasks at task index is less than or equal to workers at worker index plus the strength that we're adding with the pill, we can then append to our task queue. Okay, this seems completely right. Task queue that append tasks at task index, yeah. Incremented by 1. However, if not task queue, yeah, return false. If task queue at index 0 is less than or equal to workers at worker index, we know we have to pop left from the task queue. But if the remaining pills we have is if we still have remaining pills, we will, see what the error is here. So I should actually just pop here. I shouldn't pop left if we still have more pills remaining, because that indicates that I can still add a pill or use a pill and add that strength to my current worker to complete this task. And so I don't pop left from the task queue as one of my stronger workers because I'm adding or using the pill for the current worker. So it's just task queue.pop, and then I decrement the number of pills we have remaining by 1 because I did use a pill there. So now I think this should be accepted. Now I think this should actually work, unless I made another very silly error here, which I really hope I didn't do, or rather I should say. I see what else I did here. So this should be left plus right plus 1. This is just a very simple summing error for me. Obviously, we know that the mid value is not going to be left plus right divided by 2, at least not standardly. It's going to actually be left plus right plus 1 divided by 2 to actually get that accurately. Let's go ahead and check if that works. And as you can see, this really is just about as efficient as you can get it to be. As you can see, well, it beats 92.4% of users runtime-wise. It's a 400 millisecond complexity. And for memory, it beats about 40% of users, taking about 26 megabytes of memory. And this is the most efficient solution to solve this problem in a very elegant way, right? So on a high level, how are we really solving this problem? Kind of just glossing over what we said before when we were explaining it. Effectively, we're kind of combining binary search with that greedy strategy helper function, and basically by sorting both tasks and the workers, we can obviously make more optimal assignments for which workers get which tasks, because of course we want to prioritize the stronger workers to not use pills for them and get them to get the stronger tasks. And also using that kind of double-ended queue allows us to actually efficiently manage both of the tasks from both ends if we want to use pills or not for the weaker workers, and that's very important to actually whether to actually assign a task directly or use a pill. We'd rather use a pill for the weaker workers to get more amount of workers who can actually do tasks, unless the stronger workers still need pills to do even the weakest of tasks. And we also have to actually do this in the most efficient way solution. Hence, the reason why binary search is the way to go, because binary search is just known to be more efficient because it is a logarithmic runtime complexity, which brings us to the complexity of our solution. So for the runtime complexity here, it is honestly really complicated. There's just a lot going on. There's a lot of different algorithm implementations. On a high level, in the worst case, the overall runtime complexity is going to be big O of n log n plus m log n plus the minimum of n and m, and that's going to be multiplied by the log of the minimum of n and m. That probably didn't make much sense. Let me just quickly type it out here. So for the runtime, let me just comment it out as well. Runtime complexity, I'll let it equal sign so it doesn't get too confusing. It's going to be big O of n log n. This is going to be added by m log m. This is then going to be added by the minimum of n and m. That's then going to be multiplied by log of the minimum of n and m. Let's kind of break through why this actually is. So, to actually sort the tasks and workers, we know sorting is an n log n operation. So to sort both tasks and workers, it's going to be big O of n log n plus m log m. Of course, that's because n is the number of tasks and m is the number of workers. The actual binary search, again, we talked about it. It's going to be logarithmic. It's going to be big O of log of the minimum of n and m, right? Minimum because that's kind of a higher end pointer or right initial pointer. And for each binary search iteration, we know we actually do use that can aside function here. That's going to run in big O of k, where k is basically the current midpoint. And so that's why we get that kind of long complexity for our runtime. And for our memory complexity, don't worry, it's a lot easier. I won't even type it out. It's very just straightforwardly big O of k, right? Why? Because we're using that double-ended queue as our extra data structure or our auxiliary memory to store up to k tasks. And so the space complexity or memory complexity is big O of k, which technically is really just big O of m, or rather the minimum of n or m in the worst case, right, for the memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.